All right, what did we do last time? What did we do? We did the argument principle. The argument principle. I guess that we did the time before. We saw applications of the argument principle. Argument principle says you integrate f prime over f. That counts zeros minus poles with multiplicity. Right? That's the amazing thing about f prime over f, is that you don't have to, there's no residue to compute. The residue is 1 if it's a 0 and -1 if it's a pole with multiplicity. So that amazing thing gave us Rouché's theorem. If f is strictly larger than g on the boundary of a disk, then number of zeros of f inside the disk is equal to the number of zeros of g inside the disk. That was Rouchet. We also did open mapping theorem. Open mapping theorem. If you have a holomorphic function, the image of an open set, unlike real valued functions, is open, and the maximum modulus principle.
Number of zeros of f is the same as number of zeros of f plus g, right?
Thank you very much. Thank you. I'm glad someone's paying attention. And the maximum modulus principle, how should I put this? There does not exist, well, let's say like this. If there exists a z0 in omega such that for all z in omega, f of z is at most f of z0, then f is constant. Okay, if you have a holomorphic function on a region and there's some point that is where it's greater than all the other potential points, then the function, in other words, really the contrapositive. If f is not constant, then there's not a maximum inside the region. The maximum is achieved on the boundary. If it's, if it's continued, if it can be continued to the boundary. Okay, and then we talked about homotopy, right? We got all the way to the definition, but maybe not the proof of, still without the Jordan curve theorem, the proof of independence of the integral on the homotopy class. So definition, let's remember this. If gamma 0 and gamma 1 are two curves in a region, here's a region, here's gamma 0, here's gamma 1, they have the same starting point. So gamma 0, let's say they're both maps, from 0 to 1. So they start at the same place and they end at the same place. Let's call this maybe alpha and this beta. So this is alpha and that's beta. These two curves with the same starting and end points are homotopic if there exists a homotopy. If there exists a map from S in 0 to 1 cross T in 0 to 1 to omega, which is jointly continuous for all S, gamma S of 0 is alpha. They all start at alpha. They all end at beta. And gamma restricted to S equals 0 is gamma 0. Gamma restricted to S equals 1 is gamma 1. Okay, so if there's this smooth family of curves, always going from alpha to beta, that interpolate between gamma 0 and gamma 1, then gamma 0 and gamma 1 are called homotopic. Okay, so far so good. And theorem, Did we state this theorem, or am I stating it for the first time? It doesn't matter. It's not so hard to state a theorem. If f is holomorphic on omega, and I have two curves, gamma 0, gamma 1 in omega, are homotopic, then the integral of f over gamma 0 is the same as that over gamma 1. Okay? Not so surprising. It's formalizing a principle that we've been dancing around. But notice, we have not said anything about Jordan curves. I'm not talking about insides or outsides or whatever. Right, this will have the consequence. I'm getting ahead of myself. We'll talk about the consequence in a minute. Okay, so proof. Let gamma be the homotopy, a homotopy. Be a homotopy. Okay, so again, we've lost our picture. Here's gamma 0, here's gamma 1. And gamma is, well, it's this whole thing kind of filled in by curves. So this region, this is compact. Let's give this a name. It's the 2 torus. Let me not, you know what I mean, it's not really the 2 torus because there's no, it's just compact. Let's not give it a name. So gamma is a homotopy. I claim, well, I think this is easy. The image gamma of this whole region is compact. Let's call this K. Okay, so K is this whole image. Right? Image of if you have a continuous function, takes compact sets to compact sets. Why? Nick?
Continuous means preimage of an open set is open. So if you, in your image, you take an open cover, you pull it back to an open cover of your first thing, which has a finite subcover.
Perfect.
And then you're done.
Yeah, take an open cover of K. The pre-image of that will be open because omega is continuous, gamma is continuous, and now you have an open cover of this compact set, which means you only needed finitely many, and then just choose those finitely many and they will cover K. Do I need to write that out? Maybe, no, okay. Yeah, we've seen this point set topology stuff before. Right, so what does that mean? So this image is compact. For every point in the image, this is something else we've seen. The complement of gamma, let me say it like this. The omega complement is closed. Omega is an open set, an open domain, and it's disjoint from K, which is compact. So the distance between these things is positive. Let's call it 3 epsilon. Okay, this is closed, this is compact, and the intersection is empty. So there's a distance between them. Do we need to review that? We've used this before. This is a standard argument. Okay, what I'm saying is around i.e. for all points in K, the disk of, there exists an epsilon, there exists this, so there exists an epsilon such that this holds. So for the disk of radius, let's call it 3 epsilon around omega is contained in big omega. Okay, so for every point W, there's this disk of radius epsilon, 3 epsilon around W that still stays inside your domain omega. Okay, So fix that epsilon. Fix this epsilon. Fix this epsilon. Now, big omega is jointly continuous. Continuous in the S and T variable, right? So here's the S and T variable. This is S from 0 to 1. This is T from 0 to 1. And so the preimage of some little open set is some little open set in S and T. And it's jointly continuous, and the domain is compact, and hence it's uniformly continuous. What does that mean? Given epsilon, such as this epsilon, there exists delta independent of S and T, such that for all, let's say S1 and S2 differing by delta, and for all T1 and T2 differing by delta, the image gamma S1 T1 minus gamma S2 T2 is less than epsilon. Let's read this. Let's read this. We have these curves, right? These families of curves, gamma S1, gamma S2, they're parametrized by points T. So here's T1 and here's T2. So I've taken some S1, S2 here and some T1, T2 here, and this little rectangle maps onto where, well, these 2 points. I mean, I'm taking sort of S1, T1 and S2, T2 and seeing where do these 2 points map. They map to a distance of at most epsilon.
Professor?
Please.
Why not sum of the two absolute quantities be less than delta?
So uniform continuity says
No, that is fine. Like I'm asking, why not absolute of S1 minus S2 plus absolute of T1 minus T2 less than delta?
You could do that too. Same thing. I'm using, instead of circles, I'm using the Archimedean. Instead of an Archimedean norm, I'm using an L infinity norm. Squares and circles are both what's it called? Units for what they both generate the open sets.
Is it a basis?
A basis, thank you. That's the word I'm looking for. A basis for Borel sets. Yeah, so you could say, you know, I want the sum of the squares of S1 and S2 plus the square of S1 minus S2 plus the square of T1 minus T2 to be less than delta or less than delta squared, or whatever. It doesn't matter what regions you choose. Okay, so we have an epsilon. That's the epsilon that allows us to stay within omega for all time. We have a delta. The delta comes from uniform continuity, so the delta doesn't depend on the location of S and T. This holds uniformly for all S and for all T. As long as the S's change by no more than delta and the T's change by no more than delta, then the value of gamma from one curve to the other at these different points changes by no more than epsilon. In particular, if I don't need this this second part of it. In particular, if I just use the same T for all S1 minus S2 less than delta, and for all T in 0, 1, I have that gamma S1T minus gamma S2T is less than epsilon. Okay? So what I will claim, so I'm just setting T1 equal to T2, in which case their difference is definitely less than delta. This is setting T1 equals T2 equals T. So my claim is that the integral over gamma S1 of f is equal to the integral over gamma S2 of f. This is, again, for S1 minus S2 less than delta. So I have this, I mean, there's the bigger picture of omega, gamma 0, and gamma 1. And what I'm saying is, if I change s by at most delta, it doesn't change the values of the integrals. And what that means is I can go from gamma 0 to gamma delta, then from gamma delta to gamma 2 delta, and so on. And in 1 over delta operations, I walk my way from, so in 1 over delta steps, walk from integral over gamma 0 to being equal to integral over gamma delta, being equal to, and so on, until I get to the integral of gamma 1. Okay, does that make sense? If I can prove this claim. Okay. Now let's look at this claim. So for each t in 0, 1, I can take a ball of radius, consider the disk of radius 2 epsilon around gamma S1 of t. Okay, so let me draw another version of this same picture. So here's our starting and end points. This is gamma S1, gamma S2. And for every point t, I draw a ball of radius 2 epsilon around gamma S1 of t. So this is the disk of radius 2 epsilon around gamma S1 of t. First thing is, this stays inside omega because the way epsilon was chosen was so that you had a disk of radius 3 epsilon around every point and still stayed inside omega. If you remember how we chose epsilon, way back here. Way back here. Okay, so epsilon was chosen to make sure that when I take a disk of radius 2 epsilon, I'm still well within omega. Okay, that same epsilon reaches, since this is 2 epsilon, the point gamma S2t is inside this disk. Okay, and therefore as t ranges, so as t ranges over 0, 1, what we have is this gives these disks cover the image of omega on S1 to S2 cross 0, 1, which is compact. You see what I'm doing? I take a disk at every value of t, which also contains the value of t on gamma of S2, because this distance is at most epsilon. And so as I change disks, I get all these disks. I get uncountably many of them. And they cover this continuous image of a compact set, which is compact. And so I only need finitely many such disks. This is compact, so only need finitely many disks. many disks, let's say D0 through Dn. Let's make it n plus 1. Okay, so now I have these disks. Here's D0 and here's D1, and they're centered at these points. T's, it doesn't matter what the, let's not call the T's. And here's the last one, Dn plus 1. Okay, and let's take, well, let's do a slightly simpler version of the argument. There's a more complicated thing in the book that I don't actually like as much. On D0, D0 is a nice disk. F is holomorphic, so it has a primitive. Let's say capital F, 0. Holomorphic functions on disks have primitives. So we have this primitive F0. On D1, F is holomorphic and has a primitive F1. So that's on here. On D0 intersect D1, we have two primitives. F0 prime is equal to F1 prime. And so F0 is equal to F1 plus some constant. Okay. Replace F1 by F1 minus this constant. That's still a primitive. Still a primitive on D1. And now F1 is an analytic continuation of F0, since they exactly agree on the intersection. F1 is an analytic continuation of F0 to D0 union D1. So we always have a primitive on a disk. Now we have a primitive on the union of two disks. And of course, when we continue all the way out to the last disk, so continue extending analytically to the last disk. Which means we have a primitive, which means we have a question?
Yeah. What if I take F to be 1 over Z and I'm going around the unit circle?
So
I know I don't have a primitive that is defined around the entire circle because it will be multiple valued at some point.
yes, the curves will not be homotopic in the region where F is. We're getting to that example. That's the next example I want to discuss.
Okay.
So the assumption is F is holomorphic. In the region, there's this big region omega. F is holomorphic on omega.
Okay, so what if I take my region omega to be, say, the deleted unit disk, and my one curve is the unit circle? I guess I have to take maybe the two unit disk.
Sure.
So that but deleted, so I take away the 0.
Yep.
My one curve is precisely the unit circle, and the other one shares a point, but is just deformed somewhere. Nothing wild.
Yeah.
How does this work where I can, of course I can locally write down a primitive to F anywhere along the circle.
Yeah.
But I can't wrap it around to a primitive on the entire unit circle.
So what you're saying this, let's come back to, let me just finish the proof.
Sure.
And then we're gonna do exactly the argument that you're discussing.
Okay.
So no, I see your point. Yeah, this is not. I see your point. If I want to deform, I see your point. Let's look at your point. Let's look at your point. You're saying take a disk of radius 2. We want to delete the origin and take a circle of this size and then take some deformation of that circle. And my argument would say that f does have a primitive on this region, but I didn't say that these endpoints are different. And so now I seem to be constructing a primitive on an entire domain. So where's the problem with this argument? So I'll tell you what the book's argument is. The book's argument is something that is a little bit more complicated, and I didn't like it. So where's the problem with this argument? So let me tell you the book's argument, and then we can analyze them together. Ozan, you want to say something? No. The book's argument is a bit simpler, if you like. Simpler, if you like. So certainly we have, on each disk, we have a primitive. No question about that. So they'll take a point, let's call this Z1 and W1, on the intersection of the two disks. Is there something in the chat? Oh, your mic's not working. Do you want to try to type it or? Okay. Well, maybe while you type, I'll keep going and then I'll keep an eye out for what it says. So, right. So we're going to take these points on the intersections. So Z1, this will be Z2, this will be W2, and this will be, let's say, Zn and Wn, while Ozan is typing. Okay, and the total integral, let me get rid of this. So the integral over gamma 2 of f is the integral from alpha to Z1 plus the integral from Z1 to Z2 plus and so on, up to the integral from Zn to beta. Okay, I'll draw another version of the same picture. Here's alpha, here's beta, here's Z1, which is inside D0 and D1, and so on up until Zn, which is inside Dn and Dn plus 1. And then and the same thing is true for, sorry, this is S1 and S2. This is S1 and S2. But on S2, we go through this point W1. So we'll go from alpha to W1, then from W1 to W2, all the way up to the last point, which will be Wn to beta. Okay, so we're just adding up this segment plus this segment plus this segment plus that segment will be all of these. Now, on each segment, the idea of form primitive reductively by adding, which I agree with, primitive have it in. You can do this because the primitive is unique up to constant. You just change the constant. The problem is in the intersection can be disjoint open sets, and the constants can differ between them. The intersection can be disjoint open sets. The intersection between consecutive disks, you mean? Between this disk and that disk. So, I mean, I'm taking a sequence of t values where the disks are centered and taking disks at those values in such a way that there's always overlap. So let's see where this argument will not produce, so this argument is not trying to argue that there's a global primitive, yeah, if they loop around. Right, if it loops around, that's the real question. If it loops around, so here's S1 and here's S2. And now I'm making disks. There's disk D1, D0, and disk D1, and disk D2, and so on. And here's the last disk, Dn plus 1.
I think when you loop around, you have to make Dn plus 1 also agree with D1, but the primitive you get for Dn plus 1 to agree with D1 may not be the thing which you constructed from D1 to Dn plus 1.
That's
So if you take
right.
the example of 1 by z.
No, of course,
add a
of
2
course.
pi.
We're all saying the same thing. There's
That's
no
the manifold.
reason. Well, yeah, really what's happening is we're creating the Riemann surface of the logarithm function when we unwrap this. So let's just do the book's argument, which is cleaner from this point of view, but somehow less intuitive. Yeah, it's like I mean, it is a sheaf argument. This analytic extension is where sheaves came from. All right, so let's just finish it, and we'll come back to what's going on. So on this first integral takes place inside D0. So on this first integral, there's a primitive, F0 is a primitive on D0, primitive on D0. So this integral of f from alpha to z1 is f0 of z1 minus f0 of alpha. And similarly, the integral from alpha up to w1 of f is f0 of w1 minus f0 of alpha. Right? So that's just on those two curves. And then we're going to add on to this the integral from z1 to z2, which now is of f, which is f1 of z2 minus f1 of z1. So now I'm on the second piece. Now I'm on the second little piece, and I have a primitive f1. This is a primitive in D1. And similarly, there's an integral from W1 to W2. Big F1 of F is big F1 of W2 minus big F1 of W1. And the primitives differ by a constant. No problem with that. I'm not trying to make a uniform primitive, but on two disks, the primitives differ by a constant. When I add these two things, so let's see, let's take the sum of these two, excuse me, and the difference of these two. What do we see? We get, so I'm subtracting these two things, and I'm subtracting these two things from these two things. So the top is f0 z1 minus f0 of alpha plus f1 of z2 minus f1 of z1. That was just the top row. The bottom row is minus f0 of w1 minus f0 of alpha minus f1 of w2 minus f1 of w1. So I'm just adding this plus this minus that. And look at what's happened. So first of all, these two are canceled. And now I'm asking about, let's group it like this, f0 at z1 minus f1 of z1. That's a constant. which is the constant by which the primitive changes from disk 0 to disk 1. And then I have minus f0 of w1 plus f1 of, so you see, I have f0 minus f1 is a constant, and here I have minus f0 plus f1 at the same point. So this is minus a constant. And so the sum of these two things, is f1 of z2, the only thing that's left over, minus f1 of w2. And now you continue by induction. Continue, and the partial sums of, from alpha to z1 to z2 up to zn, minus, over all these integrals, minus the sums of alpha to w1 up to wn, will be the last, it's the last fn at zn plus 1 minus the last fn at wn plus 1. But here's alpha, here's z1, here's zn, and here's w1, and here's wn, and zn plus 1 and wn plus 1 are the same point. So at the end, they come together again. And when we added up all the segments, the error that we got, the cohomology, was this f1 of w2 minus f1 of z2. And at the end, they come back together. And so the total error is 0. All right. So what does that mean? What we've shown is that the integral over S1 is equal to the integral over S2. Whenever S1 and S2 are so close that the curves always stay within an epsilon ball of each other, so that we can cover it by 2 epsilon balls, which are small enough so that 3 epsilon balls stay inside omega. That was the basic argument. And this is true whenever they differ by delta. And so you go from gamma 0 to gamma 2 delta up to gamma 1 in 1 over delta steps, and therefore the integral over gamma 0 is equal to the integral over gamma 1 whenever f is holomorphic and 2 curves are homotopic in the region. Now, all right, maybe this is a good time to take a break and analyze the argument in the case that Nick pointed out. Let's do that. Okay, so, all right, next, so definition. I mean, exactly to avoid this kind of stuff, definition, region omega is simply connected if for every pair of curves lying in omega with, going from alpha to beta. In other words, having the same endpoints and having the same initial point and having the same endpoint, they are homotopic. For all pair with the same endpoints, with same endpoints, they are homotopic. They are homotopic. Okay. Great. Let's just do a couple of simple examples. Example: any convex set is simply connected. Why is a convex set simply connected? What does it mean to be convex?
We can take a line between the points and it stays in the
Yep.
set.
A linear combination, a convex combination, except I can't call them different letters. So for all t in 0, 1, this thing is in omega. Okay, so whenever you have omega, if you have a point z and you have a point w, then the line through them, so this is not convex, the line through them needs to be entirely contained in omega. Why is this simply connected? So given a curve gamma 0 and gamma 1 with same endpoints from alpha to beta, what is my parametrization S cross T?
Well, you can just linearly interpolate pointwise.
Exactly, linearly interpolate. You take gamma 0 of T times S, I guess times 1 minus S, to make this right, plus S times gamma 1 of T. That will always be in omega. These are continuous. These are continuous functions, jointly continuous. So is jointly continuous, has the right endpoints because it's linear combinations of fixed endpoints at 0 and 1, is jointly continuous, and hence a homotopy. Is a homotopy. Okay, here's another example. The so-called split plane. In other words, you take 0 down to minus infinity away, and I claim this is simply connected. It's definitely not convex, right? I take this point and this point, the line through them is not, I guess I want to do it like this. Take this point and this point, the line through them is not in the set. So if I have two curves with the same starting and end points, how am I to, this is gamma 0, this is gamma 1, how am I to deform one to the other?
There's probably some like bijection with the half plane.
Yes, with, well, there is with the half plane, but there's an easier thing to do, which is to biject with a strip. So r e to the I theta, let's say gamma 0 of t, we can write as r of t e to the I theta of t, where theta will always be between minus pi and pi. And the same is true for, so let's call this r0 theta 0. And the same is true for gamma 1 of t, r1 of t e to the I theta 1 of t. And so what we really are doing is taking 0 infinity, this is r, cross minus pi pi, this is theta. And this strip is simply connected. This is the r theta plane from minus pi to pi. This half strip is simply connected. Is convex. Is convex. So you could take something like gamma 0, so let gamma s of t be. So I want a convex combination of these things, it's clear what to do in the argument, e to the I guess 1 minus s theta 0 of t plus s theta 1 of t. That will definitely interpolate the argument. And now I want to interpolate the real part. It doesn't really matter how I do this as long as I stay away from 0. So this will be just as good as anything else. R0 of t plus s times R1 of t. Or you could do this multiplicatively if you like. You could do or R0 to the 1 minus s times R1 to the s. These are real numbers, powers of real numbers. No funny business yet. Anyway, I'm just sure there's no reason to really parameterize this. I'm just giving you some examples of why things can be simply connected. Any questions? Everything makes sense? Keep going? Yeah, okay. So some corollaries. So theorem, if F is holomorphic on a simply connected region, then F has a primitive. Proof, let big F of z be the integral from z0 to z of F. This is independent of the path because any two curves, any two paths are homotopic. And we just proved that the integral is the same if the two curves are homotopic. Simply connected means every two curves with the same starting and endpoints are homotopic. Okay, and our standard argument will show that f prime of z is f. So you zoom in to take the derivative, you zoom in, and so you're in a little ball, and so you can take the straight line. Zoom in near z, so f of z plus h minus f of z is a straight line from z to z plus h. F of w dw, dot, dot, dot. Okay? So let's prove, does this make sense? And now here's a nice theorem. How do you prove something isn't simply connected?
The integral depends on the endpoint. In the past,
Yeah, how do you show that there's not? How do you show?
I think what you're saying, Saram, is there's no primitive.
Yes. Well,
Or rather, there's a holomorphic function on that set with no primitive.
so let me put it another way, and hence the integral over any closed curve of f is 0. Because if you have a primitive, then the integral is just the primitive evaluated at the two endpoints. If the two endpoints are the same, then the integral over a closed curve is 0. And the proof of this theorem is if it was simply connected, then the integral
1 by z
over the unit circle, this is the unit disk, unit circle, of exactly dw over w would be 0. This is a closed integral, but we know that it's not. I always say 2 equals pi equals I equals 1, not equals 0. Okay. These two things are not equal. So you're proving topology using analysis. Okay. Proving a statement in topology, topological statement, using analysis. All right, it's fine to exhibit a homotopy. How do you know a homotopy doesn't exist? That there's no way to exhibit a homotopy? Well, if it did, that's what you get. Bless you. Okay, fine. We're almost up to complex logs. I think we're up to complex logs. So any questions at this point?
Random question. What do you call a set that is not connected, but any two paths that share endpoints are homotopic?
It's
Like-
not connected.
Like basically something that's just a disjoint union of simply connected sets. Is there like a name for a set?
You can be
that's like-
simply connected without being connected.
Oh, so they are actually okay.
Simply connected just means any two curves with the same endpoints are homotopic.
Okay, I assumed it was that and it was connected.
So
But-
it's not, yeah.
Okay.
So, remark can be simply connected without being connected. So simply connected, when you want to check if two curves are homotopic, you assume that they're the same endpoints. Here you assume gamma 0 and gamma 1 map alpha to beta. I mean, not map, are a path from alpha to beta. And they're continuous. So everything's taking place in connected components. So the question is all of these questions, question of homotopy is in a connected component. So this omega is simply connected. Any two curves are homotopic. It's vacuous that about a curve from here to here because no curves exist from here to here. Okay. Vacuous otherwise, since no curves exist. No curves, continuous curves exist between disconnected components. Okay, great. Let's get to the complex logarithm. So we would love complex log. What we want too much, basically. We want log of z1, z2 to be log of z1 plus log of z2. And we want log of r e to the I theta to be, so this would be the complex log. This should be the real log of r plus I theta. And you can't have both. Can't have both. Well, in a sense, you sort of can't have either. Well, okay, if we restrict this to minus pi pi, then you can have this. Okay, so let's talk about that. Let's just state a theorem. let omega be simply connected. Assume that 1 is inside omega. Assume that 0 is not inside omega. Okay, so here's 1, here's 0. Whatever omega is, it needs to be simply connected and contain 1 and not 0. Then there exists a function f of z, which you can think of as log on omega of z, holomorphic on z, on omega, such that f prime of z is 1 over z, e to the f of z is z. Good. And 3, you see we have this neighborhood around 1. There's a disk around 1. So if you take f of r, where I'm looking on the disk of radius epsilon around 1, intersect the real line, this will be the usual real logarithm of r. So there exists an epsilon such that. So on this real, so in a neighborhood of 1, you get the real logarithm back. And the proof is very simple. Okay, is the statement clear? Yeah, the proof is very simple. Proof, let f of z be the integral from 1 to z of dw over w. It's well defined. Well defined. It's independent of the choice, independent of the path, since omega is simply connected. This formula is proved as always. So 1 follows from our usual things. 1 is, let's just say, clear. 2, let's look at 2. For 2, let's look at this function, z times e to the minus f of z. And let's differentiate this. So product rule, derivative of z is 1, e to the minus f of z, plus z times the derivative of e to the minus f of z is e to the minus f of z times minus f prime of z. F prime is one over z. That cancels that. We're away from z equals 0. 0 is not in the region. And so the derivative is zero. And so z times e to the minus f of z is a constant. And the question is, what constant is it? Let's evaluate it at z equals 1. So now we get 1 times e to the minus f of 1. F of 1 is an integral from 1 to 1 of something. You integrate over a constant curve, you get 0. So the constant is 1. So z times e to the minus f of z is 1. In other words, e to the f of z is z. So that proves 2. How about 3? So there's a ball. There's a region where this is contained inside omega. Omega is open, so around 1 there's some disk. If I intersect with the real line, I'm supposed to get the real logarithm.
I guess it's got to follow from 1 and the agreement of like differentiation in the complex case with the restricted to the real case.
Yeah, all I want to do, if I'm near 1 and R being real, just take the horizontal line. Take your gamma to be horizontal line. Horizontal. So big F of Z will be the integral, now really from 1 to R, of dx over x. Which is the definition of the real logarithm. Does that make sense? So in other words, we could take whatever curve we want to get from 1 to R, but don't be a dummy, just take the straight line. You're staying in the real line, and what you're integrating is dx over x. That is the real logarithm. Okay? Any questions? So that was a check mark for number 3. Right, let's say definition, when omega is this slit plane, which is simply connected. It's simply connected. Connected. 1 is in the slit plane, 0 is not in the sim plane. That means we have a log of omega is called the principal branch. Principal branch of log. And we will write this as just log. So if I write log without specifying anything further, and we're talking about complex analysis, I mean the principal branch. It's best to always specify that you mean the principal branch. There are lots of times where you don't want the principal branch, and lots of theorems get in trouble when they try to do something and they mean 2 different branches at the same time. Okay. All right. Yeah, so here's a corollary. For z equals r e to the I theta in this split plane, this log, this principal log, is indeed equal to log r plus I theta. And here I mean this is in minus pi pi. How can we prove this? So here's the split plane. We're taking away 0 and the negative real line. And we have some point, which is r e to the I theta. And we're supposed to start at 1. So remember, big F of z, this log on omega, is the integral from 1 to the point r e to the I theta somehow, dw over w.
First go horizontally, then go vertically.
Yes, exactly. The right path to take is to first go horizontally over to R, and then go vertically, and then go, sorry, did you say vertically? And then go axially, rotate up to angle theta. So let's try this. So this is really, so integral over omega, over gamma rather, is an integral over gamma 1, which is the real part, plus the integral over gamma 2, which is this bit. And let's see what that is. Integral over gamma 1, how do we parameterize on gamma 1? Z equals x, x ranges from 1 to r, and I have an integral from 1 to r dx over x. That is indeed the real log of r. And how about the integral over gamma 2? So on gamma 2, that's this bit, this radial bit, z is equal to r e to the I theta. R is fixed. Theta ranges from 0. Oh, I can't call it theta. Phi. Phi ranges from 0 to theta. Phi is this angle, ranging from 0 to theta, possibly minus, but the sign will take care of itself. So I have an integral from 0 to theta, 1 over z, 1 over r e to the I phi, z dz, so z prime, r e to the I phi times I d phi. Okay, so on this branch, the sum of this and this is exactly what we wanted. So we get it on that branch, but other places we get in trouble. All right, we'll have to stop there for today. Any questions?